Accurate real estate valuation is the absolute bedrock of market liquidity and financial stability. It determines exactly how much capital can safely flow through the physical environment. An entire ecosystem depends on the precision of these figures. Buyers and sellers require them, investors calculate project feasibility, lenders underwrite mortgages, and governments assess the taxes that fund public infrastructure. When valuations decouple from reality, the macroeconomic consequences are severe. Systemic overvaluation obscures the true risk in lending portfolios, artificially inflating asset bubbles across the broader economy. We saw this exact vulnerability during the 2008 subprime mortgage crisis. Flawed, overly optimistic valuation models allowed capital to flow into assets that could never support the debt, leading to massive defaults and a global freeze. Historically, establishing value required slow, manual workflows. Appraisers physically inspected properties, analyzed lagging historical sales data, and applied subjective professional judgment to arrive at a final number. Today, that old manual approach is overwhelmed. The modern real estate market produces complex, high-dimensional data, from real-time interest rate fluctuations to minute-by-minute shifts in local economic indicators at a volume human analysts cannot manually process. Because it relies on historical comparisons and manual analysis, traditional valuation is inherently a lagging indicator. In fast-moving financial markets, looking exclusively in the rearview mirror introduces critical systemic risk. The real estate industry is now rapidly transitioning away from static paper documents toward dynamic, real-time automated valuation models. Artificial intelligence does not rewrite the fundamental economic laws of supply, demand, and utility that govern real estate. The underlying math of property value remains the same. Instead, AI functions by executing those traditional formulas using datasets and processing frequencies that were previously impossible for human teams. The core structural shift is AI's ability to ingest, quantify, and price unstructured data. Information trapped in property photos, municipal zoning documents, and local news reports can now be converted into exact numerical variables. This integration applies directly to the three pillars of the industry: comparative market analysis, income capitalization, and the cost approach. For institutional capital, adopting these algorithmic pipelines is no longer an optional upgrade, but a structural necessity for maintaining market competitiveness. The comparative market analysis, or CMA, relies on the substitution principle. It estimates a property's value by comparing it to similar properties that have recently sold in the exact same market. The traditional bottleneck here is human subjectivity. An appraiser typically selects 3 to 5 comparable properties and relies on their personal judgment to adjust the baseline value for physical differences. Manually guessing the exact dollar premium of a specific feature introduces statistical weakness. A human analyst cannot objectively prove that an extra bathroom adds exactly $15,000 to a property's value without introducing bias. Machine learning removes this guesswork. Instead of comparing 3 homes, an algorithm can instantly process tens of thousands of recent property transactions across an entire region. This enables what is known as a hedonic pricing model. A hedonic pricing model is a statistical method that breaks a property down into its individual features and mathematically estimates the specific market value of each one. By cross-referencing thousands of sales, this mathematical model isolates individual variables. It calculates the exact bias-free market premium of a renovated kitchen, an extra bedroom, or proximity to a transit station. As new transactions close, the model dynamically re-weights these feature premiums in real time, ensuring the valuation reflects today's buyer behavior, not last quarter's. Through machine learning, the comparative market analysis transforms from a subjective human estimate into a rigorous, high-confidence data pipeline. For commercial properties, the gold standard is the income capitalization approach. This method values a property strictly based on the future cash flows it is expected to generate. This is the foundational formula. Property value equals net operating income divided by the capitalization rate. The numerator represents the cash coming in, and the denominator represents the required rate of return. This formula is highly sensitive. Because it relies on division, a microscopic human error in setting a static cap rate will drastically skew the final multi-million-dollar valuation. Predictive analytics solves this by dynamically adjusting the cap rate denominator. The AI continuously feeds real-time macroeconomic indicators, like inflation metrics, bond yields, and employment data, directly into the formula. To calculate the numerator, algorithms project net operating income by looking beyond historical ledgers and toward external market signals. They do this using natural language processing, or NLP. NLP is a branch of artificial intelligence that allows computers to understand, interpret, and extract data from human text and speech. The NLP model parses unstructured data across the market, reading local news articles, scanning municipal zoning documents, and analyzing social sentiment to forecast commercial vacancy risks before they materialize on a balance sheet. By continuously updating both the income projections and the rate of return, AI converts income capitalization from a static snapshot into a living, forward-looking financial model. The cost approach assumes a buyer will not pay more for a property than the cost to build an equivalent structure. The equation is straightforward: land value plus replacement cost minus depreciation. The traditional limitation here is calculating that depreciation. Accurately estimating physical deterioration usually requires an appraiser to conduct a costly manual on-site inspection. To process unstructured visual data without a site visit, the industry uses convolutional neural networks, or CNNs. CNNs are deep learning algorithms specifically designed to recognize complex patterns and objects within digital images. These neural networks analyze listing photos, drone footage, and satellite imagery to grade property conditions objectively. The AI scans pixels to detect physical wear and tear. It can identify water stains, measure shingle deterioration on a roof, and automatically flag structural risks for the valuation model. Simultaneously, the network identifies value-add renovations. It recognizes the specific materials used in updated kitchens or bathrooms and adjusts the replacement cost calculation accordingly. By digitizing the visual assessment, computer vision can quantify physical depreciation with mathematical precision, significantly reducing the reliance on manual on-site visits. Beyond the physical building, a property's value is heavily dictated by its broader spatial and environmental context in the market. To measure this, models rely on geospatial analysis. Geospatial analysis is the computational method of mapping, analyzing, and interpreting data tied to specific geographic coordinates. This technology merges high-resolution satellite imagery with AI to evaluate land characteristics alongside municipal zoning regulations. The model maps a property's precise proximity to vital economic drivers, calculating the exact distance to transportation hubs, shipping routes, and commercial centers. At the same time, it calculates the property's exposure to long-term environmental threats, cross-referencing location data against shifting floodplains, coastal erosion rates, and wildfire zones. Institutional portfolios use this spatial data to run automated stress tests. They can simulate severe climate events or sudden zoning changes across thousands of localized assets simultaneously. Geospatial AI allows the market to quantify previously invisible environmental hazards and price those long-term risks directly into an asset's current valuation. When you integrate machine learning comps, dynamic income capitalization, computer vision, and geospatial analysis, you get the modern automated valuation model, or AVM. Modern AVMs generate valuations at a higher frequency than human appraisers. They are highly scalable across massive portfolios and devoid of traditional human subjectivity. Because they operate purely on statistics, these models must mathematically grade their own outputs. They generate a confidence score, providing operators with a precise percentage indicating how reliable the valuation is based on the available data. However, an AVM is critically dependent on that underlying data. When tasked with assessing highly unique, custom, or historic properties where comparable data is scarce, the model's accuracy degrades. AVMs are also vulnerable during periods of rapid market volatility. Because they train on historical patterns, sudden economic shocks can render their predictive forecasts inaccurate. This creates the black box problem. The black box problem is a scenario in artificial intelligence where an algorithm outputs a result, but its internal mathematical pathways are so complex they are effectively hidden from the human operator. An AVM's output provides a powerful baseline, but if financial institutions follow these algorithms without oversight, those hidden mechanics introduce new systemic risks to the market. Because of these algorithmic blind spots and strict data dependencies, artificial intelligence does not replace the fundamental need for human appraisers and analysts. Instead, it forces an evolution. The real estate professional is transitioning from a manual data gatherer into an algorithmic auditor and high-level market strategist. The ultimate strategic advantage in modern real estate lies in synthesis, combining high-speed algorithmic baselines with nuanced human oversight and judgment. This human-in-the-loop approach mitigates the black box risk. Analysts verify the AI's logic, adjust for real-world context the model missed, and capture market value that algorithms cannot see. This synergy achieved between software and human judgment allows for a level of pricing accuracy and market liquidity that neither could achieve in isolation. AI has rewritten the mechanics of valuation. Moving forward, the market belongs exclusively to the professionals who know how to command these algorithmic outputs to navigate an increasingly complex financial landscape.